Okay, so I will talk about the hypoelliptic Laplacian. So first of all, I'm a short-term visitor here, and I've been working on the subject for about 12 years. So I will have to compress in 1 hour a number of things. So I apologize about that. So let me try to explain, first of all, what is the idea. Well, the idea is I will describe an interpolation between two natural gadgets which live in different categories. The first object is a Laplacian. Whatever Laplacian you know, whether the Hodge Laplacian, the Laplace-Beltrami Laplacian, Laplacian-Dolbeau's theory, on one hand, and on the other hand, I will have a dynamical system, which is typically the geodesic flow. And the interpolation will be by operators which will act on a bigger space. So you interpolate between two gadgets which are not in the same category. So this is already strange. But nevertheless, this interpolation will have a number of interesting properties that I will explain in the course of the talk. So here is the organization of the talk. First of all, elliptic versus hypoelliptic. I will explain briefly what is hypoellipticity here. I will review the case of S1. Then I will move to the trace formula as an example of application of the concepts and ideas coming from this. Then I will review a proof of the Riemann-Roch-Grothendieck theorem in Botchan cohomology. So this is more algebraic geometry oriented. And then I will give a conclusion. Okay, so first of all, elliptic operators. As you know, differential operator P is elliptic if its principal symbol sigma of x and xi is invertible for xi non-zero. So the principal symbol is very easily obtained from the operator itself. So let me give you the basic example. If x is a Riemannian manifold, and you take delta x to be the Laplace-Beltrami operator, then minus delta x with a proper sign is an elliptic operator whose principal symbol is xi square. So another example is Laplacian on the circle. Special case with symbol xi square. And the fundamental thing is about ellipticity is that it's stable. If you start from an elliptic operator and you deform it a little bit, it's elliptic. Now, what I will promote here is exactly the opposite idea, that ellipticity is an extremely unstable concept, and that actually ellipticity sits just at the border, at the verge of hypoellipticity. So this deformation, immediately you move to the hypoelliptic world when you move. Okay, so the price for this motion, for this idea, is that in effect you will have to change space. So what is a hypoelliptic operator? So first of all, hypoellipticity is a weaker property. So, there is a sort of formal definition of hypoellipticity which doesn't say much, that a differential operator P is hypoelliptic if when acting on a distribution. If you get something Pu is C infinity on some open set, then U is still C infinity on the same open set. So this, of course, elliptic operators are hypoelliptic. Hypoelliptic, hypos means less than elliptic. Okay, so a typical example, probably historically the first example, is the operator of Kolmogorov, introduced in 1934, which is an operator in two variables, x and y. And the first, of course, it's not elliptic because it doesn't differentiate twice in the x variable, but still it's hypoelliptic. So it is in some sense the model of the hypoelliptic operators studied later on by Hermander. And this Kolmogorov operator will stay very much in the background. So what is the main statement again? So I start from x, a Riemannian manifold, and I call delta x the Laplacian on x. So the main statement is the elliptic operator minus delta x over 2. So 1 over 2 is a distracting normalization on x, can be deformed to a family of hypoelliptic operators LB indexed by the parameter b, acting on the bigger space. So it acts on the total space, typically of the tangent, or if you like, of the cotangent bundle. So this LB act on a bigger space. They are hypoelliptic, and this family interpolates between the original Laplacian for b equals to 0 and the vector field, in this case the vector field, the generator of the geodesic flow for B equals infinity. So you have these two kinds of things, second order operator acting on the base X, dynamical system, vector field acting on the total space of the tangent bundle, and this LB interpolate between these two gadgets. These operators again act on this bigger space. So let me make a remark. The statement does not make any sense because the operators do not act on different spaces. So we cannot really say in what sense, precisely for the moment, in what sense this is an interpolation. However, eventually, when we will be able to make sense, when we are able to make sense out of this, if we are able to make sense out of this, it will eventually connect objects of analysis to geometric objects. Well, more generally, the theory will connect the Laplacian with any Hamiltonian dynamical system, proper dynamical system, but this I will skip. So let me just explain, first of all, how does LB look like. So even if you don't understand anything of the talk, I will just show you what is the formula for this operator LB. So I introduce the space X script, the total space of Tx of the tangent bundle. So I introduce, first of all, the first operator which just acts fiber-wise. Okay, so you have this big space, the fibers which are the tangent bundle, and I first of all introduce a well-known self-adjoint non-negative operator along the fiber, which is just the so-called harmonic oscillator along the fibers Tx. So this is a universal object that you can associate to any Euclidean vector space. And then the second thing I introduce is the geodesic flow as a vector field on the space X script. So Z is a vector field, and if you like, if you take geodesic coordinates on the base at this precise point, the vector field Z is just the sum of yi d over dxi, right? So it should be clear that the element y here is the generic element in the fiber. So you get this way a vector field, and y squared is just the norm of this generic element. So the hypoelliptic Laplacian, essentially, it's a weighted sum of these two objects. The first is the harmonic oscillator along the fiber, and the second is the geodesic flow. And there are other lower order terms which contain essentially geometric terms that I will not comment about for the moment, but this is a general structure of the hypoelliptic Laplacian. So by Hermonda, what we know is that this operator LB is hypoelliptic, and more precisely, it has a heat kernel, which is stronger than that. So the operator d over dt plus LB is hypoelliptic. So let's observe that these two operators, H and Z, are as canonical as the Laplacian. In the same way as the Riemannian manifold carries the Laplacian, the hypoelliptic Laplacian is also carried by any Riemannian manifold. So the operator LB has appeared, of course, before. It is known as a transport operator or a Fokker-Planck operator in the case of a flat space R3. So what is our goal? Our goal is to show that this deformation that I'm talking about is obtained actually by deforming the underlying analytic and geometric structures. That is, it's not only just purely the operator as a Laplacian that we deform. We deform all the underlying geometric analytic structure, like, for instance, Hodge theory. In certain cases, we will see that the full spectrum of the original operator, of the original self-adjoint operator, Laplacian elliptic, is preserved by the deformation. So this is completely counterintuitive that in this deformation, part of the spectrum in certain situations can be preserved. So I will review three examples: the case of the circle S1, the case of the trace formula, Zellberg's trace formula for locally symmetric spaces, and when finally I will outline an application in complex algebraic geometry, the proof of the Riemann-Roch-Grothendieck theorem in Bott-Schoen cohomology. So there are two underlying key ideas in this. The first is index theory, which will permeate the whole talk, even if, albeit in implicit form. And also the idea of the Fourier transform, the hypoelliptic Laplacian will turn out to be a way of encoding a geometric version of Fourier transform. So let me just mention, first of all, why is the case of S1 important? Well, because closed geodesics, in some sense, are modeled on S1. And since, for instance, the trace formula, we know that closed geodesics play an important role in the formula, the case of S1, in some sense, is the model case that we should study first. So one should expect that for S1, the deformation is trivial, and we will see that this is not entirely the case. So let me start the case of S1 by elementary considerations. So I start with the equality 1 plus 1 equals 2, which is probably the hardest thing that I will state in my talk, but just also to mention that the number 2 will play an important role. You already saw it in minus delta x over 2, and 2 will be essentially everywhere. So you could construct my talk just a talk on this number. The second identity is the identity for the sum a plus b squared. The third identity is the identity for the integral of the Gaussian distribution. And so the fourth identity, which is slightly more significant, is the computation of the Fourier transform of the Gaussian distribution. So let me review the proof of this last identity, because in some sense it will play an important role later on. So what you do is that you reduce squares, and then at some point you perform an imaginary translation of the variable y in the purely imaginary direction while using analyticity of the Gaussian distribution. So this, in some sense, we will do later on in an infinite dimensional context. So we've used Fourier and analyticity. So let me go back again now to the harmonic oscillator in one dimension, in the variable y, h. So it is well known. This is an operator which is essentially self-adjoint elliptic and whose spectrum is given by the integers. So the ground state of the harmonic oscillator, corresponding to the zero eigenvalue, is exactly the Gaussian I was dealing with before. So let me now make a formal translation. So first of all, the hypoelliptic Laplacian in this case is an operator in two variables, x and y. X, you can think of it as lying in R, or eventually on an S1, and y lies in the tangent bundle to R, or the tangent bundle to S1. So here is the operator LB. In this case, it is just the harmonic oscillator in b divided by b squared minus y over b d over dx. This operator here should be thought of as being the generator of the geodesic flow. So we do, in some sense, exactly the same reduction of squares as we did in the computation of the Fourier transform. That is, we combine the y squared with y d over dx, and we get something like this. So what we want to do then is make a formal translation y gives y plus b d over dx. So why do we want to do this? Because if you are doing Fourier in the variable x, d over dx would be replaced by ixi. And so that formal translation would be exactly y gives y plus b ixi. The problem with this translation is that imaginary translations do not act on smooth functions of y. They do not act on Sobolev functions of y. Basically, they only act on analytic functions of y. So anyway, doing this translation is the same thing as conjugating the operator LB. So what do I mean by this? So a conjugation of LB now. So first of all, I introduced the cross derivative operator, M. This is a cross derivative in x and y. This is a hyperbolic operator. So that its exponential does not act on anything. I mean, it's certainly completely unbounded. I mean, it doesn't make any sense. However, what I'm saying is that you can write a conjugation identity. I mean, in some sense, this conjugation identity should be viewed in the space of operators with polynomial coefficients, so that for the moment it is purely Campbell-Hausdorff-like or formal conjugation, which says that conjugation the operator LB by an operator which does not exist as an operator, you now get a nice operator which is, first of all, elliptic, which is self-adjoint, and in which the variable x and y have decoupled. So that we find that in the LB, the original hypoelliptic operator, is formally conjugate by a conjugation which does not make sense to an elliptic operator, which is, in some sense, much simpler. So why is this important? Is that if we were able to make sense of the conjugation, in particular, the two operators would be isospectral. So that's precisely the case. The conjugation is legitimate. So again, let's take xy in S1 cross R now. So what I'm saying is that by analyticity, even though imaginary translation in the variable y does not act on smooth functions of y or does not act on any Sobolev space, it acts on the eigenfunctions of the harmonic oscillator. The eigenfunctions of the harmonic oscillator are all actually analytic functions. The ground state, as I mentioned, is the Gaussian distribution, and the other ones are just products of the Gaussian function by polynomials. So that in some sense, the operator LB can be, in some sense, in this situation, explicitly diagonalized. And what you find ultimately is that the isospectrality property holds true, even though the intertwining map between the two operators is an extremely unbounded operator, not acting on no reasonable space other than the space of analytic functions. So what is the consequence of this? So let's look at the operator LB again. This is, as you see, non-elliptic, non-self-adjoint. It has a self-adjoint piece, which is the first one, and a skew-adjoint here. And what you find is that the spectrum of this operator is exactly made of two pieces. There is a piece which moves around, which is the integers divided by b squared. The integers is the contribution of the harmonic oscillator. And there is a rigid piece. This corresponds to the spectrum of the Laplacian of S1. So the important thing to keep in mind is this rigidity. And also, by the way, also the fact that the spectrum remains real, although as b tends to infinity, the antisymmetric piece of the operator takes over. So something like this could never be true in finite dimensions. So again, I pointed out that the spectrum of the original Laplacian remains rigidly embedded. And this is a phenomenon which will hold true actually in the context of locally symmetric spaces when replacing eventually S1 by a locally symmetric space. So, no, it's not. This phenomenon of rigidity is not a general Riemannian phenomenon. The origin of rigidity actually is cohomological, and I will try to explain this later on, that it is cohomology and, in a certain way, index theory, which explains completely the rigidity. So let's observe also that when b tends to 0, if you look at the spectrum here, when b tends to 0, all the eigenvalues go to infinity except precisely the contribution 0 corresponding to the ground state of the harmonic oscillator, which means that from a spectral point of view, I can see that the LB converges in the spectral sense to the Laplacian on the base. So we already have a hint of this convergence, and more generally, it will be exactly a convergence of this kind. So Poisson formula now. So we can use supersymmetry to eliminate actually the annoying part of the spectrum, this one which moves around n over b square, and there is dans, this is just a French word which floats around the talk. I'm sorry about this. So we use supersymmetry to eliminate n over b square, that is to eliminate n over b square, except of course a zero eigenvalue. So I actually introduce the exterior algebra in one dimension and the corresponding number operator which acts like 0 on 0 forms and 1 on 1 forms. And what I do, I just now, instead of looking at the operator LB acting on functions, I always make it act on differential forms. Of course, the spectrum is unchanged, and you should remember this operator LB. I'm sure you will remember it, but in due time, I will remind it to you. So what you ultimately get is the following formula, just from all the computations I did, which is that the trace of the original heat operator on S1 is equal to the difference of traces, supertrace, of the heat operator for LB. So in some sense, you're able still to compute something spectrally about the original Laplacian using the hypoelliptic operator LB, so that by making B tend to infinity, you can get a proof of Poisson formula by interpolation. The reason for this is that the operator LB, when B tends to infinity, the geodesic flow part becomes dominant. The heat propagates more and more along geodesics. So if you work this out, you can prove the Poisson formula by interpolation. And this will be actually later on the model we will give of the proof of Zellberg's trace formula by a similar interpolation. Now, let me go to trace formula as a Lefschetz formula. So I take X to be a compact Riemannian manifold. I just look at my watch. And I introduce delta X, again, the Laplace-Beltrami operator. So the heat operator acts on smooth function X, smooth real function on X. So what I will do is simply, viewing this as a picture that is not taking the heat operator too seriously. First of all, I will pretend that the heat operator is an element of a group. Well, okay, it's a semi-group. Of course, this I know. But, if you're introducing an I in front of it, doing some weak rotation, you would have a group of unitary operators. So anyway, there are many ways in which we can legitimately consider that G is an element of a group. Actually, the corresponding Lie algebra would be the Lie algebra of differential operators, say, on the manifold with a proper reservation. Taking into account all the difficulties there is in making sense out of it. So we call it G. We call the heat operator G. So what we are going to do now is think of the space of smooth functions, smooth real functions, as being the cohomology of some complex. Okay, so of course any vector space is the cohomology of itself. So this is not, making a too crude assumption, but so that means that it's a cohomology of an acyclic complex RD, so D is a differential, R is a complex.
You got two R's here, but they're very different, right?
One is bold-faced and the other not, I guess. If you try to catch me on these, I will be in trouble. I will be in serious trouble. So you'll have to accept that R and R are not the same thing. Yeah. So what this means is that actually the smooth functions are just the H0 of this complex, and the higher cohomology vanishes. So let's imagine this. So that actually the problem of computing the trace of the heat kernel on the smooth functions becomes the computation of the trace of the group element, G, on the cohomology of a complex. So, it requires a new dignity in some sense. It becomes sort of cocky. The only problem is that for the moment there is no complex at all. So remark again that contrary to what we do usually with cohomology of compact manifolds, since the space of smooth functions is infinite dimensional, this cohomology will have to be infinite dimensional. So 2 questions. First of all, is it true that we can view the space of smooth functions on a manifold as the cohomology of something natural, say? And the second thing is that we would like also this group element to act not only on the smooth functions, but also on the full complex. Okay, so why is that? Because, I mean, what we're going to ask is more precisely this. Is there a Dirac-like operator dr acting now on the complex, not on the space of smooth functions, but on the complex itself, so that we would have something like an index-like formula. Okay, so when you are in finite dimensions, basically, let's say you take the classical Euler characteristic. So you can evaluate the Euler characteristic in 2 ways. First of all, using just the dimension, alternate dimension of the cohomology, but also introducing the Hodge complex, looking at the whole spectral theory decomposition, and actually viewing the original Euler characteristic as an alternate sum of traces. This is a basic index theoretic formalism. So we want to find, in some sense, an equality of this type, that the trace of G acting on the smooth functions would be equal to the alternate sum of traces of G times the exponential minus d squared r over 2b squared. Sorry, no, this is getting uncontrollable, so sorry. I have to go back. Okay. Yeah. Okay, so I should not move here. So it will be, this equality would be the strict analog of the formula of Makin and Singer, which is used in the proof of the index theorem and more generally of the Lefschetz fixed points formula of Atiyah and Bott. Of course, the main point is that since the original cohomology is already infinite dimensional, this operator dr will sort of be a sort of second quantized Dirac operator. And this is exactly what eventually we will be able to do later on. So let's first of all explain that the answer to the question, is this possible to do this and that, is yes. So let me just show to you in what sense the space of smooth functions on a manifold can be viewed as the cohomology of something natural. So you take E, a real vector bundle on X, you call E script the total space of the vector bundle, and you embed the manifold X into a script as the 0 section of a script. So what I'm doing is I'm just looking at the Dirac complex along the fibers. Okay, so I don't look at the whole differential forms, I just look at those differential forms along the fibers of E, equipped with the fiber-wise Dirac operator. So this is a complex, and its cohomology, by just using the Poincaré lemma, is just the space, the original space of smooth functions on X with values in R. So that in effect R resolves the space of smooth functions. It exactly sits, the cohomology of this complex is concentrated degree 0, it is just the space of smooth functions. On the other hand, the answer to my previous question is no, because in general the heat operator, which has acting on the space of smooth function, does not lift sort of naturally on this resolution, and there is in general no Dirac operator dr commuting with G, etc., etc., etc. So I will now review the case of locally symmetric spaces to explain why in this case it is possible to give a positive answer to this question. So let me take X to be locally symmetric. So locally symmetric means that you obtain it, yes?
Is it important that it's compact?
No, it's not important because I mean, eventually what we will do is evaluate orbital integrals. And not, I mean, in some sense, we will just work upstairs on the before taking the quotient by gamma. But I just prefer to reformulate it this way for the moment. Okay, so I take for the moment X to be a compact, locally symmetric space. So the Casimir operator coming from the group is in the center of the so-called universal enveloping algebra of G. So this Casimir operator acts on the smooth functions precisely like the Laplace-Beltrami operator, and basically tends to act on everything. So this question of having an operator whose action does not lift naturally is, this objection is over. So there is some hope. So the problem is to construct the Dirac operator dr. So I will now go back to the case of S1 again. So on the case of S1, there is a chance that I will understand what I say. When I will go to the case of general symmetric or locally symmetric spaces, things will be slightly more involved. So let's go into the case of S1 first of all. So our operators will act on smooth functions of S on cross R with values in the exterior algebra of R. So I introduce the following operator dB. It's an operator in two variables, again, acting on the exterior algebra of R, not of R2, but of R. So the first piece is minus dx plus d star x. dx is the theorem, d star x, you know what it is. The second piece, okay, now I have to take this on again. Yes, okay. So the second piece is essentially a Witten-like theorem Hodge Laplacian. That is, you recognize here dy plus y, which is the Witten twist of the operator dy, plus its adjoint. So the only thing which has to be taken into account is that dx is equal to dy. In other words, there is only one exterior algebra. There is not two. There are one. There is dx and dy are the same. Okay, so again, dy plus y wedge is just a Witten twist of dy. Actually, in some sense, the operator d plus y gives you a version of a resolution of the space of smooth functions, because what I said before was valid for the classical Poincaré lemma. Here you use a twisted version of Poincaré lemma in which actually the function 1 is replaced by the Gaussian function. And here is the operator LB. So this is the abstract construction. I give it, the formula is minus half of d squared over dx squared plus half of db squared. So dB will be our sort of second quantized Dirac operator. So let's look at what the formula is for LB. If we compute LB, we exactly get the original operator I obtain in the case of S1. Again, you know, it comes back like a dream, maybe a nightmare, but you see again appearing the harmonic oscillating variable y here. Here is the generator of the geodesic flow, and here is the number operator divided by b squared. So I had established before this identity. This identity was established by bare hands computation. Sorry, I have to go back here. Okay. This was the identity, the trace of the original heat kernel is equal to the super trace of the hypoelliptic heat kernel. Now, if I use the formula that I gave before for LB, I just rewrite it this way. Trace of the original heat operator is equal to the super trace of G, G being the exponential of heat kernel, exponential minus T d squared B over 2. It's just rewriting this in this way. And this is a strict analog of the McKean-Singer formula. Okay. So I've now been able to give a cohomological sense, the proper cohomological sense of this simple computation in the case of S1, in some sense to put it already in the context of classical index theory formula, but with, in some sense, cohomology, which is now infinite dimensional. So let me now explain how to do this in the case of locally symmetric spaces. So I take G to be a reductive group, like SL2R, K a maximal compact, and X equal G over K, the symmetric space. I will also use the Cartan splitting of the Lie algebra G script equals P plus K. So the Lie algebra carries an invariant bilinear form, which is positive on the P part and negative on the K part. So, by analogy, the space Rx, original space R in the variable X, will be replaced by the Lie group G. And Ry will be replaced by the Lie algebra. So before we had S1 cross R or R cross R, now we have G cross the Lie algebra. Okay, the operator minus dx plus d star x will be replaced by a well-known operator introduced by Kostant, the operator d hat k. I will briefly describe it. The operator d hat k had mostly algebraic interpretation, and now it will play a key analytic role. One should also treat differently p and k because of this change of sign on the killing or the invariant form, so that actually the, if you like, second quantized Dirac operator dB will be made of the sum of three terms. You should not look at this. Do not look at this one. The first part is an operator acting on G, on the group. That's the Kostant operator. The last piece here is essentially a version of the twisted Witten complex along P plus K, but for some reason I will not explain. I have to treat differently the P and K part to take into account the fact that the bilinear form is positive on one of them and negative on the other. So analytically there is a slight different treatment. And there is finally a third piece here, which is the real hero, because if the third piece here was not there, the theory was just be destroyed. And this actually is already a quadratic piece. So d hat k is the Dirac operator of Kostant, as I already said. So let me just say what briefly the Dirac operator of Kostant is. So when Dirac introduced the operator, Dirac operator, he was trying to find a covariant square root of the ordinary Laplacian. In some sense, the Kostant operator is doing this for the Casimir operator. You have the Casimir operator acting on a group, and the Kostant operator is essentially a square root which is differential operator, a square root of the Casimir. So actually, you have to introduce the Clifford algebra C hat of G associated with the invariant form B. I will need to use, but you can forget about it, the fact that the exterior algebra of G star is acted upon by the Clifford algebra. Okay, there is some three form here. Just forget about this. I just give briefly the description of the operator d hat k. So d hat k is a section of the product of Clifford algebra times universal algebra. Here is a classical Dirac operator part, and here there is a cubic correction. In the literature, this operator is often called the cubic Dirac operator. So the remarkable property is that the square of this operator is a scalar operator. It is exactly, essentially, up to universal constant, the Casimir, or minus the Casimir. So this identity is just the analog of minus dx plus d star x square is equal to d square over dx square. That's exactly the analog. So what is now our operator dB again? I just rewrote the formula here. So LB is 1/2 of minus d hat square plus dB square, exactly the same structure as in the case of S1. So this was the analog formula in the case of S1. And now the last thing, and that's the point where we probably are lost, is that you have to need to descend everything to x, to the quotient by k. In other words, for the moment I did the construction on G cross the Lie algebra. And now I have to descend everything to the quotient by k. But because the constructions I gave are covariant, they descend properly. So let me just explain on what space our operators will act now. So the original symmetric space, x equals g over k, carries a bundle which is bigger than Tx actually. It is Tx plus its natural complement, which is modeled on the Lie algebra splitting P plus K. So in other words, the tangent bundle to a symmetric space is a homogeneous bundle modeled on P, but there is another bundle which is modeled on K. And so actually, our new hypoelliptic Laplacian will act on the total space not of Tx, I'm sorry, but of Tx plus n. On the,
N again? I don't understand N.
so n, okay, K, the group K, acts by the adjoint representation, both on the P part and the K part. When you make it act on the P part, you get the tangent bundle. When you make it act on the K part, you get its orthonormal complement. Let me give an analogy. When you have the sphere, you have the tangent bundle, you have the normal bundle. The direct sum of the two is a flat bundle. That's R3. That's a strict analog. On any symmetric space or locally symmetric space, there is a natural complement which makes the direct sum flat. So our operators will act now on smooth sections over X script of the twist of this full exterior algebra. So let me just briefly mention this. That I describe these operators acting on a bigger space. But if instead of making the operators act on a bigger space, you can instead view the operators acting on an infinite dimensional bundle on the base manifold. In other words, using the Bargmann isomorphism. The Bargmann isomorphism says that the L2 space of an Euclidean vector space is the same thing as the completed polynomial space, vector space of polynomials on the vector space. So this is the identification. L2 of Tx is the same thing as a symmetric algebra of T star x. That's through the Hermite polynomials. So that actually, instead of viewing the operators acting on a big space, you can instead view them as acting on an infinite dimensional vector bundle now, on the symmetric space X, which is a tensor product of the symmetric algebra and the exterior algebra. Okay, this is of fundamental nature in the theory because, as we know, the symmetric algebra and the exterior algebra are twins, even though we do not always know it, but they know. So the geometric picture of enlarging the space is equivalent to a representation theoretic picture of taking infinite dimensional vector bundles over the symmetric space. So let me now give a formula for the operator LBX. Okay, so this is a formula. So again, it's an operator acting on the total space of Tx plus n. Now, I wrote in red here, again, the harmonic oscillator along the fiber of Tx plus n. Tx plus n is a Euclidean vector bundle. I do have here the geodesic vector field acting on this total space. And finally, there is a quadratic, a piece of degree 4, which plays an essential role in the theory, but which makes that in some sense we're starting to deviate from the classical theory I outlined before, just having the harmonic oscillator. This piece here is just you take the Lie bracket of these yn and ytx. Y has two components, one in n and tx. This is modeled on p and k, so you can take the Lie bracket, you get an element of tx, and you take the norm square.
This formula is
It's the same.
It is the same.
Yeah, it is the
What
formula.
showed us, many slides back.
I mean, I gave the formula of LB as being minus 1/2 of d hat square plus db square, which you do the computation, you get this. That's the result of the computation. Okay, once you do the computation and go down to x, you get this operator. This formula is just the analog of what I got in the case of S1. In the case of S1, I was getting the harmonic oscillator here, plus this one here, and just plus, I was getting just what is in red. And now I get a bunch of other terms that I don't explain to you. These are matrix-like terms. And what I'm saying is that the operator LBX deforms the original Casimir operator acting on smooth functions. It deforms exactly in the same sense as the case of S1. Okay, of course, I mean, one could say that it's a strange idea of a deformation because these deformations are not visual deformations. You're not going to see just by looking on the face of this operator that it deforms the original operator. Okay, that's an abstract deformation.
So in what sense is this a deformation?
In the sense that if you were doing, say, from a spectral point of view, okay, if we were trying, we now would be on a compact base, we'd look at the spectral theory, I would say that you would have exactly the same sort of convergence as b tend to 0 of the spectrum of LBX as b tend to 0 to the spectrum of the base Laplacian, exactly in the same way as you have it in the case of S1.
So you need to have all these other terms.
You need to have all these, I mean, what you want, you remember this, that you want to have a deformation in which the original spectrum remains rigidly embedded. So these other terms, you know, they might look as a nuisance. I mean, if you want to have an exact formula, you need everything. Okay, so let me again now take a look at a symmetric space, which is compact. So we have the identity, which is a strict analog of what I had before in the case of S1. The trace of the original heat operate on functions. The Laplacian is just twisted by a constant, is equal to the supertrace of the hypoelliptic heat kernel acting on this big space. But actually, when you have a locally symmetric space, you can express the trace of the heat kernel as a sum over the conjugacy classes of the pi1 of the heat kernel universal cover. This is just a Poisson-like, the original Poisson-like formula. So that actually this identity can be broken down into an equality of the contributions up there on the symmetric space. So that ultimately, actually, the identity breaks down actually to an identity of semi-simple orbital integrals. So I won't go much into this, but essentially over the symmetric space, I mean, even the orbital integral can be, if you take gamma as semi-simple element, you just look at the quotient of G by its centralizer. And this is an orbital integral where PT is, say, the heat kernel on the symmetric space. Okay, this can be made sense of, so this is what you're interested in. So the orbital integral makes sense. One can understand why it makes sense from a geometric point of view, because you introduce x of gamma. So x of gamma is the symmetric space associated with the centralizer of gamma. Okay, so you have the symmetric space associated with G. Inside of it, there is a symmetric space associated with the centralizer of gamma, which is a totally geodesic submanifold of X. So an orbital integral, it is what? You just take a normal here, you take its image by gamma, and you integrate the heat kernel from here to here. The distance between this point here and the point here grows linearly, and using the Gaussian decay of the heat kernel in symmetric space, you get essentially a Gaussian-like integral. So what I'm saying is that they are, in the same way as they are elliptic orbital integrals, they are hypoelliptic orbital integrals, in which now there is some I mean, you add over this, over the symmetric space, this bundle Tx plus n, or you like the infinite dimensional bundle, so that eventually the identity becomes an identity of orbital integrals. Here is the elliptic one, and here is the hypoelliptic one. And now, of course, the idea is to make b tend to infinity, because when b tends to infinity, we hope that the operator LB will behave more and more like the geodesic floor. Okay, so this you can do. The orbital integral eventually localizes near x of gamma. I mean, there are analytic difficulties connected with the hyperbolicity of the geodesic floor that you have to find. But eventually, you get a formula for the orbital integral, which is the strict analog of Lefschetz's fixed point formulas. And it's a strict analog because it has been obtained exactly in the same sort of algebraic formulas. So I will probably skip this. I introduce a terrible function.
I have a question.
Yeah, yeah.
In this way, you're not, I didn't understand. I mean, do you still have to write the heat kernel downstairs?
No.
As a sum of the heat kernel upstairs?
Yeah.
No. You're
Eventually,
writing
you see, I'm saying that the identity that we had downstairs breaks down, it splits.
that-
So you-
down, I didn't understand it.
Because the trace down here is a sum indexed by the group gamma. And I'm saying that the deformation not only preserves the sum, but it preserves the individual pieces.
Ah, that's the
It preserves individual pieces, so you can work
yeah.
directly on the non-compact thing. Okay, so basically this makes that the orbital integral is eventually expressed as an integral over the k part of the Lie algebra of the centralizer. Take a semi-simple element gamma. Its Lie algebra splits into a p and a k part. And the orbital integral by this procedure will be expressed as an integral over the k part of a function which looks very much like the Atiyah-Bott function. Okay, so I will, this looks like, this is the integral, so this is analog of the A-roof genus, Todd genus, the Chern character, and so on. But I will skip this. So that the analog of Atiyah-Bott. Now, let me briefly go to Bott-Chern cohomology. So now I will state a theorem in algebraic geometry, totally independent of the hypoelliptic Laplacian, and I will show to you briefly how it can be used to prove it. So let me give myself X to be a complex manifold of dimension n. So the Bott-Chern cohomology is a refinement of the Ram cohomology. So you take PQ forms and you look at those which are closed. And instead of quotienting by the image of ds, you quotient by the image of d bar d. This is the Bott-Chern cohomology of a complex manifold. In the case of Kähler manifold, it is the same thing as the original cohomology. For non-Kähler, non-algebraic manifolds, it refines strictly on it. Okay, so we know that the refinement, there is a strict refinement. So the Bott-Chern cohomology is strictly finite at the de Rham cohomology. So let me introduce the equal part of Bott-Chern cohomology as a Dirac sum of the HPP of the complex manifold. So holomorphic vector bundles have characteristic classes in the Bott-Chern cohomology. So this is because when picking a metric on a vector bundle, its characteristic forms are sum of PP forms. And the theory of Bott and Chern says that the class in the Bott-Chern cohomology is independent of the metric. So let me state the theorem of Riemann-Roch-Grothendieck. So I give myself a proper summation of complex manifolds. Proper means the fiber is compact with fiber xs equal p minus 1 of s. And I give myself F to be a holomorphic vector bundle on M. Theorem. So the theorem says that if the so-called direct image is locally free, okay, so direct image, you can think of it as being the cohomology of the fibers with coefficients in F. if you assume that these have locally constant dimensions, so they form vector bundles, then the following identity holds. So as a picture, it is just the Riemann-Roch-Grothendieck formula. It says that the Chern character of the direct image in Bott-Chern cohomology is equal to the integral along the fiber of Todd of Tx, Ch of f, again all of this in Bott-Chern cohomology. Now, this also gives an identity for the determinant line bundle which always exists, but I will not comment upon. So let me just make a remark here that this result is known if the manifold M is scalar. I mean, it's known if it's projective. This is Riemann-Roch-Grothendieck original. It is known if M is scalar, and I claim that it extends to the non-scalar case. I mean, the methods at hand which exist to prove this, there are very few, because in non-algebraic, non-scalar thing, basically you have very few things to prove something like this, and it will turn out that the hypoelliptic Laplacian will provide us the trick to prove it. So in general, elliptic methods used in the context of Arakelov geometry do not work. I mean, I won't tell you what Arakelov geometry is, but the point is that what you try to prove a result like this, you try to prove it by using methods of local index theory, by making t tend to 0 in some heat-current expansion. It turns out that when the manifolds are non-scalar, all the expansions are singular. So you cannot prove the theorem using the original elliptic theory. It will turn out that by moving to the hypoelliptic world and moving far enough, you can make the singularity disappear. Okay, so you have something, an expansion which is singular as t tends to 0 in the elliptic world. By moving to the hypoelliptic, you can make the singularity disappear, but while still having to show that what you compute in the hypoelliptic deformation is what you wanted to compute originally in the elliptic world. So I will explain part of the construction when S is a point. When S is a point, that is when the theorem is empty, because when S is a point, there is nothing to prove. There is no Bott-Chern cohomology except the trivial one. So basically what you introduce again is a total space of the holomorphic tangent bundle Tx with fiber which I call Tx hat. And now it has a section y hat in Tx hat, which is a tautological section and which gives a corresponding section y of Tx on the base. So instead of telling you the detail of the construction, I will just explain to you 2 minutes what is exotic Hodge theory on which the construction of the hypoelliptic Laplacian will be based. So basically, what you are going to do is try to develop a Hodge theory which, instead of being based on Hermitian product of differential forms, which will be based on exterior product of differential forms. So let's do a thought experiment. First of all, we can make the intersection product of forms into a Hermitian form. That is, we can overcome the fact that it is non-symmetric by introducing some powers of I in front of it. So it becomes Hermitian form. So in this context, if I take the d bar operator of a manifold, its adjoint will be not d bar star, it will just be d. In this theory in which I base myself on intersection form, the adjoint of d bar is d. So if you form the Laplacian d bar d plus d d bar, you get 0. Which means that any Hodge theory based on the intersection form will give you the 0 as a Laplacian. And this is not so good. But in some sense, since we want to get a theory in which Laplacian will be less than elliptic, 0 is in some sense the good direction. 0 is certainly not elliptic. So actually, in some sense, what you have is essentially this. I mean, it's not very different. On the total space of this big space X script, you define an intersection form which is essentially the classical intersection form on forms on the base and the Hermitian forms on forms along the fiber, the Hermitian intersection. You have forms on total space. The bracket between the two will be essentially intersection on the base and Hermitian on the fiber. And that's enough. I mean, then if you just compute the Laplacian, you get something like this. I mean, it is not enough to prove the theorem that we want to prove. So basically, what you have to do, I just explained to you, is modify the metric on the base so that it depends on the coordinate along the fiber. So that means that you allow yourself now completely degenerate metrics on the base. Eventually, a metric which will be 0. It will be a metric multiplied by y squared. If you perform the Hodge theory in this, exactly take the d bar adjoint with respect to this exotic theory, you will get prove the Riemann-Roch-Grothendieck formula. But I think that I've overdone my time, so I will skip all the nice remarks I had organized for you, and maybe, yeah, I just say this, that from a dynamical point of view, that's dynamics corresponding to this hypoelliptic Laplacian, and dynamically the interpolation property is obvious, but this, I leave this to the experts, and I will just go to the reference list. That's it. Okay, so that's it. Thank you very much.
So what happens in the Riemann case? So
In the what there?
just a Riemann manifold.
So for Riemannian manifold, I mean, there is. So now this is a question which is relevant to my previous talk. So I did this in the, okay, in the case of a Riemannian manifold, you can deform, again, the original Hodge theory for the original D operator to an exotic Hodge theory on the total space of the tangent bundle, whose corresponding Laplacian is still of this kind. Okay, so that's exactly the same scheme. I outline here the case of Dolbeault theory. In Dirac theory, you can prove it's the same thing. And actually, of course, in general, for arbitrary manifolds, one does not expect the spectrum to be preserved. What one expects is that only certain spectral invariants are preserved. In this case, sorry?
For example.
Analytic torsion. So the analytic torsion, which is a spectral invariant which is known to be equal to Riemann-Masse torsion, is preserved by this hypoelliptic deformation. So that actually, by making B tends to infinity, one cannot prove yet. But what one finds actually is that there was a Fried conjecture which was equaling objects coming from dynamical real zeta functions to Riemann-Masse torsion. At least formally, this sort of result is a consequence of the deformation I outlined. At least formally. Okay, I absolutely want to make undertone, I mean, not to make it a statement, but from a formal point of view, it's a consequence of what I did.
What was would you repeat that again, what Fried did?
Okay, so Fried formulated a general conjecture saying that from the geodesic flow and more generally from dynamical systems on a manifold having certain hyperbolicity properties.
What kind of a manifold did you have to have? You have to have a symmetric space? Or
Yeah. I mean, no, for general, right? I mean, this is, yeah. I mean, that's, that's a statement which probably does not make even sense as it is, because it relies on the fact that the real zeta function has an analytic continuation at 0, and this is not known. In general, you don't know this analytic continuation property. But he formulated the conjecture in general. Okay. So what I'm saying is that the deformation I'm doing
in zeta function obtained from the length of the
yes,
primary.
yes, absolutely. Okay, and some, from the return map and using determinants of return maps and so on. So you need to do that, and that's a general conjecture which has been proved actually in the case of locally symmetric spaces, using the trace formula. That is, in this case, you can, in some sense, put your hand explicitly on everything using the trace formula. As I showed before,
So
in the
what is the statement, though? I didn't understand the statement.
the statement is that, let's say, a special value of the zeta function, dynamical zeta function, or combination of dynamical zeta function for the geodesic flow is equal to the analytic torsion. Okay. Now, let me give you the background to part of what I did here. Even though I look at the watch, I'm deeply aware that I'm taking on your time. What I originally was trying to do was to do a Witten deformation on the Hodge theory of the loop space. Okay, this is what I was trying to do. Witten deformation, the Hodge theory of the loop space, where the Morse function would be the energy function. Now, Witten deformation connects Hodge theory with Morse theory. The critical points of the energy functional are the closed geodesics. What we do here in this construction of the hypoelliptic Laplacian in the context of theorem theory is take a semi-classical limit of this. The Hodge theory of the loop space does not exist. I mean, probably you can make it exist in some way, but it does not exist in the right way. So by taking a semi-classical limit in the proper sense, the Hodge Laplacian of the loop space degenerates to just the original Laplacian of the manifold. And when you do the Witten deformation of the Hodge theory of the loop space, for some reason, the semi-classical limit is the hypoelliptic Laplacian. So that understood in the proper way, the hypoelliptic deformation is just a semi-classical version of the Witten deformation on the loop space. And the connection with closed geodesics is just in some sense a reflection of this 2B deformation, which would connect Hodge theory of loop space with Morse theory of the energy function. Okay, I'm not sure that this grand statement will satisfy you, Helmut. It's probably too grand to be made send off in a short time.
Well, what happens if x mod gamma is just finite void?
Sorry?
Finite void.
Okay.
That's the,
I mean, okay, so you're asking the right question in some sense. What I did is valid for semi-simple orbital integrals. Okay, so semi-simple elements are such that in some sense the displacement function of the symmetric space, if you give yourself an isometry, is the distance of x to gamma x. It has a minimizing set on precisely the symmetric space x of gamma. If you take a non-semi-simple element, this minimizing set is taken to infinity. So literally speaking, this nice, maybe nightmarish for you, but nice image for me, image of the orbital integral localizing itself on the symmetric space is now replaced by a nightmarish image of the orbital integral localizing itself at infinity. So certainly the geometry of this is more complicated. But as a matter of principle, one could say that if there is a nice way of defining the orbital integral, and we know that there is, then this nice way will be invariant under hypoelliptic deformation. Now, to tell you exactly what it will give, this I don't know. But this is, object of things to be done. It's not yet done. Okay, so yeah.
You can hope for some compactification in which you can actually see.
Yeah, you can, but certainly the compactification, for general gammas, it will be extremely, it has the complexity that it has. So you will have to fight also with this. Okay, so it will not make this any simpler.
Any other question? Okay, so let's thank our